All right, here's an old AP free response problem from 2003. Um, just before you even read it, just take a look at the diagram. You say, okay, I can see I've got this some object here hanging from a spring. I've got this other mass there. They've marked some distances, like from that to the bottom of here, right? You can guess just looking at it, you're probably going to use energy at some point because I see a spring and maybe like a height change going on. So just like first gut instincts, right? Looking at it, you might be expecting some sort of a spring and maybe something bobbing up and down on a spring, maybe some sort of some harmonic motion, sort of a thing. Just first glance at this. Okay, let's read it. An ideal spring is hung from the ceiling, and a pan of mass M is suspended from the end of the spring, stretching at a distance d as shown above, right? So before the spring stretches. A piece of clay, also of mass M, is then dropped from height h onto the pan and sticks to it. Express all answers in terms of given quantities and fundamental constants. Okay, and seeing things hit and stick together, it's a collision. Now you're thinking conservation of momentum probably. Alrighty, here we go. Determine the speed of the clay the instant it hits the pan. You're like, oh, it's going to fall distance h. We could just use kinematics if you want, right? It's going to fall with an acceleration of g, right? Okay, it's going to fall distance h, right? I think we can do that. So I'm going to go ahead and start with that. This is 2003. So here we go. So I'm just going to say I want to find the speed when it hits the pan. I'm going to do kinematics. A, V naught, V, displacement, and time. I like to list out my motion variables first. Acceleration is going to be, do you want to call down negative? Yeah, sure, why not? Negative G. V naught is 0. I want to find the final speed. I know the displacement is going to go down H, and the time, don't know. So you see I've got these four variables. I want the formula that has those four. The one that doesn't have T, that would be V squared is V naught squared plus 2a times displacement. So v is going to be the root, so that's going to be 0 because it starts from rest, of 2 times negative g times going down negative h. Two negatives are going to cancel each other. It's just going to be the root of 2gh. Okay, will be my speed when it hits the pan. All right, part B. It says find the speed of the pan after the clay strikes it, just after it strikes it. We know it hits and sticks. That's what we call a perfectly inelastic collision. If I think about outside forces, you're like, well, outside forces for my clay and pan system. Like, well, technically, let's see, gravity's pulling on the clay and gravity's pulling on the pan and the spring's pulling up on the pan. But what I'm going to do is I'm going to say that during that collision, it's a very, very quick little collision. Thunk, right? I'm going to say that those outside forces are very, very tiny compared to the force during the collision between the clay and the pan. So I'm essentially going to say, we're looking at just before it hits, just after it hits. We're going to say that the spring doesn't have a chance to stretch very far, right? So it's not going to be exerting, force to very much distance at all. And likewise for gravity. So I'm going to basically say that the momentum is going to be conserved because I'm going to say my outside impulse is small enough to ignore. So I'm going to have this momentum of the clay coming down and then the clay and the pan together moving afterwards. So I'm going to say that momentum is conserved. P naught is P final, right? And again, this is coming from integral f dt. Impulse is the change in momentum. And I'm saying that outside impulse is so relatively small over that brief period of time versus just the momentum being shifted, exchanged between the clay and the pan. So here we go. So I'm essentially going to say that's about equal to 0. So just initial is final. Initial, I've got that clay, and that has a mass m and has a velocity we just solved, root 2gh, plus the momentum of the pan, 0. This is basically I'm doing mv plus mv equals mv plus mv. You know what I'm saying? But afterwards, the two masses, they move together. They share the same final velocity. That's the speed we're trying to find, the speed after the clay hits. The mass is going to be 2m, the pan plus the clay, times that final velocity we're trying to find. So now I'll just say, look, I have an m in every term. Move the 2 over. I'm going to have root 2gh over 2 is going to be that v after the collision. All right, part C. Determine the period of the simple harmonic motion that ensues. Well, I recognize this system as a mass on a spring. And so I know the period is 2 pi root m over k, all right, is the general formula. In this case, that period is going to be 2 pi times the root. Now the mass is 2 big M, right? Big M is what they call the mass of the pan and the mass of the clay. Now I just have to figure out what that spring constant is. Well, the spring constant, we know that comes from Hooke's law. Force of a spring is negative kx, right? And there's our spring constant, that lowercase k. And you say, well, the force of the spring, we know that when we hung this pan on the spring, it settled out. Let's see here. When it's suspended, it stretches at a distance d. So I know that when that x is d, right, the stretch is d, when the force of the spring is balancing out the weight of the pan. The weight of the pan is just going to be big mg. So k is big mg over d. Again, that force would be in the opposite direction of the stretch. That's why that negative is there. That stretch is in negative d. The two negatives are going to cancel, basically, is what I'm doing here. So anyway, I always have a positive value for my spring constant. So mg over d is the spring constant. So that is going to go in here in the denominator under that radical. So let's see here. The two m's are going to cancel. Bam, bam. Invert that, what's in the radical. So it's going to be 2 pi times the root of 2d over g. Okay, and that'll be the period of my mass on the spring. All right. So now we're going to go on to part D. Part D says, can you find the distance the spring is stretched from its initial unstretched length at the moment that the speed of the pan is maximum? Okay, and then justify your answer. Okay. So, so we know that when that bit of clay hits the pan, right, the pan's going to start moving, right? And it's actually, and so the question is it going to be at its maximum speed at that point? And the answer is no. The position of the pan when the spring is like balancing out the weight of the pan, that was like equilibrium, right? Where the force of gravity is balanced out by the force of spring pulling up, right? For just the pan. But now I added this extra weight on, that extra m, the mass of the clay. So the new equilibrium position is going to be somewhat lower, right? Because now I have the weight of two masses pulling down, right? And that new equilibrium position, that's where the speed will be maximized, right? You know what I mean? So, so when I take a look at that, let's see if I can figure out a nice way of writing this. Find the distance it's stretched the moment the speed pan's maximum. I know it's going to be the new equilibrium position. I feel like almost like that's cheating. Nah. Anyway, it's going to be the new equilibrium position. And so I can say, again, K is max. And it's going to be going the fastest when the force is 0. The restoring force, that total force is 0. You know what I mean? When sigma f is 0, that's when a is 0. When acceleration is 0, that's when your force is at its biggest value. After that, the force will be going against the motion, slowing it down. You know what I mean? The sum of the force is 0. Okay, but that total force is 0. That's where a is 0. And so v is max. Okay, because you know that velocity is maximized when acceleration, the slope is 0, right? The derivative. That's how we find a maximum of the function, right? To set the derivative equal to 0. So that's it. So where the acceleration is 0, and that's where the total force is 0. So that's where v will be maximum, and therefore kinetic energy is maximum. That's what I'm saying. I didn't even have to do this. Kinetic energy is maximum. Let's just say where the total force is 0 and a is 0, that's where v is max. Okay, that makes so much more sense. And so basically I'm just going to solve for where the force is balanced. And you say, well, my forces, now I have the pan and the clay, right? And the spring balancing it out, right? And so I know that the force yanking down here, which is now going to be 2mg, right? Because the mass is 2m, the clay and the pan, has to be balanced out by the force of the spring. So basically doing this, sigma f is 0. I'm going to have the force of the spring minus 2mg balancing out to 0. The force of the spring, that's kx, you know what I mean? Negative kx in the upward direction. That's got to equal 2mg. I'm trying to find the distance it's stretched. That's the x is what I'm trying to find. So I can see that my x is going to be 2mg over k. And we found in the previous problem right here that the spring constant is mg over d. So it'd be 2mg over, in my k, mg over d. Like, okay, well, the mg is going to cancel. I'm going to end up it being 2d. All right, is going to be my stretch where I have, and that's where I have the maximum speed, is at 2d. All right, good enough. Okay, that takes us to the last part, part E. Going to go on a second sheet of paper. Que lastimas. All right, here we go. Second sheet of paper. Here we go. The clay is now removed from the pan, and the pan is returned to equilibrium. Okay, so it's back to when it's stretched, only d. A rubber ball, now also of mass m, is dropped from the same height, so it'll have the same speed when it gets there. After the collision, it bounces off the pan and you catch it so it doesn't hit it again. What's going to happen to the period of the resulting simple harmonic motion of the pan? Okay, now here is the deal. When that clay hits and sticks, right, thunk, and they move together, right? The momentum of the clay at first equals the momentum of the clay and the pan together afterwards. So you're like, oh, look, I'm doubling the mass to be like half the speed. You know what I mean? Sort of thing. Hey, doubling the mass, half the speed. That's exactly what happened, right? The speed was this, root 2gh. We got half the speed because we doubled the mass, right? And that perfectly inelastic collision. But now it's a rubber ball. It's going to bounce back up. So my momentum before is the ball going down. Afterwards, it's got to be the pan going and the ball bouncing up. Now remember, momentum is a vector. My total momentum still has to be the same amount down. But now part of it, the ball is going up. This pan is going to go faster down than it did before. And that's all true. But that's not what they're asking. They want to know about the period of the motion, the time it's going to take to oscillate. And remember, the speed you're going at has nothing to do with the period, right? Remember that over time, if there's like friction or whatever, or resistance, it'll slow down, but it still takes the same time for an oscillation, simple harmonic motion, right? So the thing is it going to be the same period then? But remember, before we had a mass of 2m because the clay was stuck to it. So this big, heavy, big, massive, lots of inertia thing where the spring is having to swing back and forth. Now we only have half the mass. It's going to be easier for that spring to swing it back and forth. It's going to whip back and forth quicker. Looking at the period for simple harmonic motion, t is 2 pi root m over k. I now have half as much mass as I had before. I did have 2m when the clay stuck to it. Now the ball bounces off. It's only going to be m. So I'm going to have, half the mass, right? So it's going to be like, 1 over root 2 times the period. Okay, so the question is, will the period be greater, smaller, or less than? It will be less. Okay, and why? Because we have less mass that we're oscillating back and forth. I'm just going to squeeze it on the same page. So there. Okay. So I'm going to say part E. I'm going to say the period will be less. Period for a mass on a spring, 2 pi root m over k. Since the ball doesn't stick, we have less mass oscillating. But the same spring force, same spring restoring it. To equilibrium. So, okay, according to this, T is less. Okay, less inertia, it's a lot easier to whip back and forth. Okay, that's it. So that's part E. Hey, that's the 2003 problem of the clay hitting the pan. Sorry about that.